Hello, today I'll be talking about Physics Lab 5, which is centered in Faraday's law. For the introduction, the objective of this experiment was to observe how a bar magnet interacted with an aluminum tube while falling through it. In an ideal scenario, this experiment would have been done with a copper tube, but since that's a bit more difficult to acquire, an aluminum tube works as well. For the physics concepts we'll discuss, mainly we'll talk about Faraday's law, Lenz's law, and magnetic fields and electric currents. I'll talk a bit more about them in the next slides. So for the experiment, the materials were a smartphone, a bar magnet, a roll of aluminum foil, and a meter stick. Firstly, we had to use the phone and the app we installed to locate where the north side of the magnet was located. Therefore, we let the magnet drop through the tube and record the time from entering to exit. So the purpose of the glow script code was to calculate analytically the time, or to predict the time that the magnet would be inside the tube from entering to exit. Here are a few snippets of code I wrote, and at the end, the result I was given was 1.8 seconds. And based from the videos on my smartphone, the real time was actually 2.2 seconds. So we can see it's very close generally, but we can attribute this difference of 4/10 probably to experimental settings or human error whenever deciding when the magnet entered. But in general, the results are very similar. Now there are a few questions I'd like to answer about the glow script code and the experiment in general. So the first one is, why does velocity change over the tube? So firstly, I want to talk about how magnetic fields are the result of electric currents. Changing a magnetic field next to a non-magnetic field will induce an electric field in a metal, which subsequently generates a magnetic field with an opposite orientation with respect to the magnet. So the magnetic field induced in the metal attracts the falling magnet, and in consequence it creates resistance. And this resistance is what ultimately slows down the magnet. So that's a more specific answer as to what we can see here in the bullet point. And also I want to talk about Lenz's law. And essentially, when our magnet is moving next to a metal, it creates the magnetic fields, but they act in a very specific way, let's say. So in a sense, they want to cancel out the magnetic field in the metal, but the metals don't like having magnetic fields in them. So essentially they move in opposite directions, and this is what it's called Lenz's law. And for the next question, so if the magnet is flipped and we reach the north and the south pole, I think ultimately the relationship between the magnet and the tube would change, because now the magnetic dipole moment would be pointing in an opposite direction. And now as for the what if questions at the end. So the first one talks about what happens if the resistivity of the conductor is as close to zero as possible. And I think that from Ohm's law, we see that current is inversely proportional to resistance. So I think a decrease in resistance would lead to an increase in current. And consequently, we could see a dramatic change in the force on the loop. So essentially, the less resistance we have in our experiment, the more current we see. And as for the second question, I think it was a very interesting one. And I think firstly it depends in the size of the holes and the cuts. So for example, if they are microscopic holes, I don't think this would change the experiment much, since it wouldn't affect the force or the resistance too much. But if we see bigger holes and bigger cuts, then since this relates to the cross-sectional area and resistance is also affected by cross-sectional area, then I think resistance would decrease and therefore current would increase as a consequence.